Let me know once it's visible.
Yeah, it's visible.
Great. So, before we move on to the coding part, the hands-on session, I'll just paint the picture slightly for the theory of quantum gain, so that even if any of you is not really aware of the topic, so we are just all on the same page yet, when we go to the hands-on session part. All right. So okay, again, quantum GANs is one of the most explored quantum machine learning algorithm, right? And again, it's the quantum counterpart of the classical GAN that was introduced in 2014 by Goodfellow and others in the paper Generative Adversarial Networks. Obviously, GAN stands for Generative Adversarial Networks. So what's going on, in a GAN? So in GAN, you don't have one but two algorithms. One is your generator and one is your discriminator, right? So what you do is to discriminator, you provide, two types of input. One is generated, input by a generator network, and the second type of input is, the real data that you have, right? And the task of discriminator is, as you might have guessed, is to discriminate the real data from the fake data. On the other hand, the task of a generator is to fool the discriminator. So to make sure that it produces the type of data where then discriminator is no longer to differentiate it from the real data, right? So when the training completes, generator has gotten so good that it's able to generate data which looks almost like the real data. And this has these efforts, for example, were a highlight were become really popular around 2018-19 for image data, where generators were just producing very real life like uh, images and human faces and stuff, and it had gotten really popular. This Gan was a model that actually paved the way for generative AI and the AI community, and got everyone really excited. Uh, right. So that's basically the anatomy of GAN. It has a generator and discriminator. Both are two different networks. You train both of them in the same training loop, right? And the task of generator is to produce such high quality data that discriminator is just not able to differentiate from the real data. Oh, what's problem with classical GAN? One, it's not easy to train. Why? Because you're not training one, but two networks at the same time, right? And it's GAN is one of those very notorious to train algorithms, right? Uh, and it's the same goes with PIN, right? Physics informed neural network that we just briefly talked about in the previous section, right? Even PIN is a notorious algorithm to train, right? Mm. It's not easy to train, the first part. The second one is how you're choosing your generator and discriminator, right? So even if you're solving a normal problem, you're just taking one network, it's still that, how many hidden layers to keep, how many neurons to keep. Those are many choices, what type of activation function. There are many choices that you have to, make. But when you have two networks coming into the same problem, you have to be very careful, right? Because the problem here is that if either of them is more powerful, so if discriminator is way more powerful, way better network than generator, then generator will just never learn, right? Because discriminator will always manage to point out the right one from the wrong ones, and this the training will not go well, right? And it is again the reason training GANs is notorious and sort of difficult, uh, right? So the first part is when you are making the choice of which network will be generator and which discriminator, it has to be made very thoughtfully, right? The third problem with vanilla GAN is mode collapse, which actually means that the GAN is not able to learn all types of data, right? It struggles there. So it can, say, so for example, you have trained it on generating the images of cats, say. So says it can produce the images of cats, but only white cats, right? It cannot produce the images of black cats or any other cats, right? So that's a more collapse, that it has only learned a certain part of the data well, right? Other things it is really bad on, right? So that's mode collapse, and it's one of the problems with GANs, right? So this was a very brief general overview of what are generative adversarial networks and what is the goal, like what's going on in a GAN, right? Types of quantum GANs, So in the previous, session, the entire thing I showed you, right? All the quantum neural networks and the entire thing that we went through, it was on that setting that, you have classical data and a quantum network. And I had told you back then that you can also have a quantum data, right? So in this problem, you are having a quantum data that will go for the hands-on session. We'll see, what it is, but so that is the reason I've chose this particular topic, because quantum GANs are explored really well. And, here we will be dealing with quantum data and not classical data. And with that, you might have guessed that, we are not having the data encoding step there in the quantum GAN, right? Because you're directly having the quantum data. Okay, let's get back to the slide. So what are types of quantum GANs? The first one, quantum data with quantum generator and quantum discriminator, right? So everything is quantum, 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 right? So you have a data type for your data set is also quantum. You have a quantum network as your generator, you have a quantum network as a discriminator, everything is quantum. The second type generally that you may see is your data is still quantum, and your generator is quantum as well, but your discriminator is classical, right? That is the second variant you may generally come across, right? And then third is again, you have a classical data and only one of the generator or discriminator is quantum. So these are the general types of quantum GANs you will come across. What we are about to deal today with is the first one, where you have data is quantum, your generator is quantum, and your discriminator is also quantum. Everything is quantum, right? The reason again, as I mentioned, for choosing this is to just show you the second type of training loop, that if you have quantum data and quantum network, how things work out. Okay, so that's pretty much it, and it's time for hands-on session. Mm, and I would say, I'll show you the code. Uh, right, it's not a problem, and I'll also send this PPT and this Jupyter notebook to the organizers. You will have all of it. So right now, I would say you can just pay attention on the code part, and while I'm explaining and running things parallelly. I hope the Google Colab is visible. Is it? It's visible, right?
Yes, it is.
Yeah, great. Uh, let me just connect to runtime first. Okay, so what is the problem statement? So we will train the quantum GAN, which has both the quantum generator is, so generator is quantum, the discriminator is quantum, and what we'll train it for is just to learn and produce a 1-qubit quantum state, right? So just a 1-qubit quantum state. It's quantum state, right? So it's quantum data, right? So the task for generator is to produce, 1-qubit quantum state, right? And it's a very simpler, naive problem, very simple problem, great for at least, first trial, right? And I do have a problem, statement that you can work on later on. And there's also a sort of assignment that you can, look for and use this implementation as, you know, what do you say, your reference, right? Okay. So I think that's the problem statement. You want a generator to reduce a 1-qubit quantum state that the quantum discriminator cannot discriminate. That's the problem statement. So for this problem setting, what do you need? The first is you need a true data, right? You need actual 1-qubit state. Then you need a quantum generator in the network. So you need to define a quantum neural network for or a quantum network for a generator, right? And then you need a discriminator, which is again a parameterized quantum circuit or a QNN or a VQC. That will be a quantum discriminator, right? Okay. So these are all the things we need to define. First comes first, let's do the installations. And as I told you, I love PyTorch a lot. I love Pennyline a lot, and they are the first choice you should go for. When you are working on with quantum machine learning, this generally your preferred tech stack should be PyTorch with Pennyline. I suppose it's your choice, but it's generally a more preferred stack. Okay, let us make the imports. The first one is obviously PyTorch, torch and module. Then we will have Pennyline, right? And don't worry, I'll explain the Pennyline part in more detail. So I understand many of you must be just having a habit of working with Qiskit, right? So I'll explain the Pennyline part at greater. I'll try to explain it greater depth. And then we just have NumPy and Matplotlib, just for plotting part. Okay, let me import them, and I've imported. It's still importing. Okay, it's done. And then I'll just set the seeds. Why? For reproducibility, right? So even if you rerun this Google Colab once I pass it to your organizing team, you will probably get the same. You'll still get the same results because the seed is set here. Okay, I'll just set the seed for both NumPy as well as PyTorch. And with that said, okay, how would you prepare the quantum state, the true quantum state, right? So you have this U3 gate. This is also a universal gate, and with this gate, we can actually reduce any given single qubit state, right? So we are using here U3 universal gate to prepare uh, given single qubit state. And how you would do that? You just set the values for theta, phi, and delta. You set the specific values, and now you have the true state, right? It's really as simple as that. Okay. So first here, let me explain what you do here. I'm just, setting some random values for phi, theta, and delta. This is the matrix representation of the U3 gate that you're seeing. And if you recall from the previous session, there we had RX gate and RY gate, they were parameterized gates as well, but they were just taking, one input as, theta. Here, U3 gate is taking three values. It's taking theta, phi, and delta, right? So this is again, I just wanted to show you that parameterized gates can have, more than just one input, right? So it would be a good exercise to again think, if in that previous quantum neural network, what if you had U3 gate instead of RY gates, right? How things would have changed, right? And how your weight matrix or weight vector would have changed, and all those steps, how would have they gone, right? So that would be a great exercise again, just replace those RY blocks with U3 gates and see what happens, right? Okay. So you have again say, you have defined these phi, theta, and delta with some values, right? Now, how you define is a quantum circuit in Pennyline is inside a function, right? So I have created this function, prepare to true state, right? And what I'm doing is I'm using Pennylanes, so QML is the alias that we use for Pennyline. I mean, just imagine how much it's focused on quantum machine learning, then the alias is QML, right? And then what you do is just simply call this QML.u3, which is obviously the U3 gate, pass in the parameters, theta, phi, and delta that you just defined, and wires are nothing but a qubit number, right? So we are applying this on qubit number 0. So, right, wires is nothing but the number of qubits. Don't be confused with that. Okay, let me run this. So we have run it. Okay, time to draw. So just drawing it is really simple. I mean, just you again have QML dot draw MPL, right? and you pass in the function. So I just passed in the entire function here, and it just drew it U3, right? Okay. So if you again recall, we have done the first part, prepare to true state. So if you see what we needed, true data, quantum generator, and discriminator. So the true data is already done. We have prepared the true state with a U3 gate. True data is done. It's time for our generator. And I bet you wouldn't have guessed this, but our generator is still the same U3 gate, right? So now what happens is you are still having the U3 gate, but your theta phi delta values are not something that you are setting. Obviously, it's just some random values which are nothing but your weights, right? And since you are using a single U3 gate, uh, your number of weights is just three, right? It's just phi, theta, and delta. That's all. Again, you want to define a quantum circuit in penny lane. What you must do, write a function here, generator, variational form, right? QML.u3 again, and you can see that I'm providing it a input weights, right? And weights of 0 becomes my theta, yes, that's theta. I'm seeing it here. Yeah, theta phi delta. So weights of 0, so the first value in the weight vector, right? Becomes the theta, weights of 1 becomes phi, weights of 2, the second or third element actually at index 2 becomes delta. Again, bias is 0, so we are talking about applying this on the qubit number 0 or the first qubit. All right, let's now implement this, run this. Okay, so this is just the generator variational form. We are defining another one with this directly encodes this, and we need this second one actually for the later part that you will see, right? So that's why we are defining two functions in the training part you'll see. And then you have generator. Again, if you want to visualize, you can visualize it, right? Notice a difference here, right? This time, when I was drawing previously, you can see I was not passing any input. I had these brackets, but there were no inputs. Why? Obviously, because the prepared true state was not taking any inputs, right? It was just directly producing the true state. Change the picture. The generator now takes the inputs weights, right? And that's why I have to provide the weight matrix if I want to draw this. Notice that I right now just I'm putting 0, 0, 0 here. But if you are generating random weights or so, accordingly, whatever weights you want to provide, you can provide, but this is what it looks like. Okay. Okay, I've run this. Okay, so we again recall we had three parts. The first part was producing true data. The second part was writing the generator. The third was discriminator. Right. So we have done the true data part. We created that true state with setting the parameters for theta phi delta for the U3 gate. Then we came on to the generator. We again used the same U3 gate, but this time we had some, just random weights as theta, phi, and delta, and that became our generator, right? And now comes the time to define discriminator. And obviously, this time you will not have the U3 gate, obviously. Reason because, you have to, the task of discriminator is to, check the right and wrong, right? Which is the real thing and which is the generated thing, which is generated data, right? So because we were having true data as a single qubit state, so it was easy to directly use U3 gate as the generator, as the architectural choice for generator. But if it was something else, then obviously you would have some bigger network. But again, for discriminator, you can't have U3 gate, obviously. You need a better network. And here we have. Okay. Again, if you see, we will define a quantum circuit for discriminator here. You can see discriminator VF, which is discriminator variational form. Again, we do the same thing. We are keeping a track of the number of parameters and how many parameters this network is introducing. Repetitions, we are setting 3. So I've tried to keep this on the same lines as the quantum circuit that I showed you in that presentation, right? The If you remember, you had 3 variational layers there, right? Okay, right. So for qubit, for now add variational layers, right? For qubit and number of for repetitions is basically the number of layer or number of times you want to repeat it. Add the variational layer one by one. So in the repetitions you're going on, so first you're repeating layer by layer. So for the first layer you will add RS gate, RY gate, and RY gate again, for in one layer. So if you recall, in that slide I showed you, you had in all the qubits you had just RY gate, RY gate, RY gate, right? But if you see here, you are not having RY gate and all of it. And for the first qubit, you are having Rx gate, and then on the second and the third qubit, you are having the RY gates, right? So you can apply this as well. That's the motto here to show you that, right? Generally, what people do is that you generally have a full, layer of RY gate followed by RZ gates. That's general thought process that people go with, right? Now, again, just but to show you that you can do it otherwise as well. And for the coding part, it's really simple, right? It's just QML.rx, just applies the Rx gate. And for the value of theta, what you're doing is just applying the weights num So yeah, weights, again, it's the input that the function is getting. The number of param is the index of the weight, a particular weight, right? And that's the reason we are incrementing number of param here. So for first layer, you will apply this because we are in the for loop for layers, right? So we will first apply the this variational layer. If you come down here, you have applying the entanglement block again, right? A simple for loop, right? Is to apply the C naught gate. So this is that entanglement block that I was showing you in that yellow box, right? So you are applying the entanglement block, and if you remember, I told you that we always like to end with a variation block, right? We don't end with a C naught block. We generally like to end with a variational block. So that's what we are doing. We repeated a certain number of times this hidden quantum hidden layer, right? So if you take these two together, this is quantum hidden layer. The alternate combination of variational layer and entanglement block. And then what we did finally, that we ended it with a final variational block. Okay, that was great. We have done it. Okay, so let's try. It's time to set and actually look at it. So and we said the number of qubits, the number of repetitions we keep to 3. You are free to chain this and play around with it. Once you have the code with you, and then let's run this. Okay, so again we have discriminator defined here, right? We again, if you see, the reason we are doing this, I mean, I will on to tell you later, but the reason is that if you see here, the discriminators just must took weights as the input here, right? If you see that discriminator VF, it's a number of qubits and repetition, a bunch of stuff as inputs, but discriminator function itself just takes in weights as the input. That is for the reason we are defining 2 functions, but we will see again in the later part once we go to the training. Okay, so we have defined discriminator function. It's time to call the simple weights. And so again, if you see here, what I did was I created some random weights, right? And based on that, I just drew the circuit and just passed on the simple weights and gave it to the model to draw, right? if you see, these are just like those variational blocks, right? If you see the first one here, this one is like the first variational block. Then you have an entanglement block, which here, because you just have a 2-qubit quantum circuit, right? You have just one C naught gate. Then you again have one variational layer, one C naught gate, one variational layer, one C naught gate, and then finally a variational layer. Now, if you see, you have set the repetition as 3. That's why you got 3 alternative, layers, right? 3 hidden layers basically, and then you ended with a final variational block. So that's the pattern that we have already seen in the presentation, right? Okay, it's time to create the Q nodes. So actually, how you create a Q node is, so actually the way you create a quantum circuit is using the Q node. What a Q node does is binds a given quantum circuit with a device, right? What is a device? It defines, what sort of device you want, right? A number of qubits and stuff. So for example, you will see here in a moment that default.qubit is what I'm using here, which is a common local simulator that provides, but you have default.mix and lightning.qubit, GPU enabled. So there are many devices, right, that the Penny SDK provides, right? So Q node object basically, binds your quantum circuit that you have defined with a particular device, which and then holds the information on the type of device itself and the number of qubits. Okay. So what we have done here is, created the measurement operator actually. I'm not sure why, but yeah, we'll see later that in the chapter where it comes. Okay, never mind. Okay, it's here itself. Okay, we are using the Hermitian operator. Okay, we are taking expectation value for the measurement operator that's defined here. All right. Okay. A very popular actually method is also, getting the output as a probability state vector. So you for that the function is qml.probs, probs, right? And that is a very popular way of getting the output as well. Here, what we are doing is just creating a you know measurement operator, right? All right, we'll define. Now, the way I said, QNode, which is basically a Python decorator here. If you don't know Python that well, you might not know what is a Python decorator. But for here, just think of it like, it takes in a function and decorates it or enhances it, and that's all, right? It binds it to something else, just makes it better or something of that sort. But it modifies it basically, right? Just think of it that way. So first part first. Here you see that you have a device, you are defining the device with qml.device, which is again Penny Lane's device framework. The default.qubit is the general, local simulator that you would generally use. Now here is the qml.qnode object that you are seeing, which is a Python decorator, as I mentioned. If you see here, interface is PyTorch, right? So you know that how well this thing, goes along with PyTorch, right? Another method, another important highlight. Differentiation method is parameter shift. So if you remember from the presentation, I had showed you, I think 3 types of, different gradient evaluation methods, differentiation methods. And I showed you parameter shift and agent differentiation and backprop, I guess. So you can actually define each one of them here, right? And the diff method of the decorator. So, you can just directly change your differentiation method by just defining the uh, keyword here in the Q node, right? Now, what we do here is discriminator with true data. So again, why we are doing this is just for the training loop, right? You will see that. So for what we'll do is first, have get the true data and discriminators prediction on that true data, right? So inside the function, what you will define that will be created step by step by the QNode object. right? So first you say prepare true data. So remember, this is the function we had defined in the very first step, the U3 gate, right? Then you have discriminator, right? So this is discriminator is just what we defined above, right? That takes in the weights and just produces that circuit, variational layer entanglement block circuit. That's what we just created right now. And every Q node object then ends with this how to extract the output part. It returns this output part, right? So here what you are doing is QML.xql, which is nothing but expectation value. Remember, we discussed this in the presentation again. What was the expectation value? I think we solved it for z observable, right? Then you're applying this, QML.Hermitian, because the operator has to be Hermitian. The measurement is just this matrix that you just created here, and you are providing the qubit number, right? So at which qubit you want this expectation value, right? So why is this zero? The zeroth qubit you want it. All right, that makes a lot of sense because your qubit state is actually prepared on the true data is prepared on the zeroth qubit. So it makes a lot of sense. Okay, so let's run this. Okay, let's run. Let's do the same thing with the discriminator now. With the generated data. So what in this function what we did was we binded the discriminator. So we prepared a circuit where you first put in true data, then you get the discriminators output on that true data. Now what you do is you have first generator, right? So it will be some generated data, and then you apply discriminator. So you will get the discriminators output on some generated data. Again, if you notice PML.Q node here, interface is defined as torch, differentiation method is still kept as parameter shift, right? Okay, let's go ahead. The final again. So let's look at both of these you know functions that we just defined. So let me just first, I mean, it's already rendered, but for the sake of rendering, I'll render it again. So if you see discriminator with true data is, so here this U3 gate that you are seeing is the true data that you have prepared. The rest of the entire thing is just your discriminator network. And if you see here, this meter symbol at the very end, this is the output layer. If you remember from the presentation I showed you, we had the same exact meter symbol there as well, right? That just denotes that you are extracting the output here, right? And remember, it's only on zeroth qubit and not the first qubit because we have defined here that the measurement is applied on the zeroth qubit only, right? All right. So that was discriminator with true data, how it looks with the generated data. Ironically, it sort of looks the same, but remember that this U3 is that random U3 gate, right? And I think I'm doing here raw MPL, but there's another variant. I mean, if I do that, you'll be able to also see the values here, I guess, but I think it's not visible right now. Or maybe I need to make a few installations here in the notebook for that to work. But never mind. I mean, I guess you'll explain it. So U3 here is that generated is it is the U3 here is the generator and not the true data. Rest of the architecture that you see is again the same discriminator network, right? Again, at the end, you see the meter symbol representing that you are extracting the output. Okay, so if you remember at the start, we told that, I mean, we need three ingredients for this training. The first is true data. Second would be the generator. The third would be discriminator. We defined all of it. So now the time is to get to the training loop, right? Okay, just a few conventions here. LD here is the loss for the discriminator. LG is the loss for generator, phi g is the state generated by generator, phi t is the true state, right? And again, if you look at the losses, these are just standard GAN losses, right? Nothing fancy, nothing quantum here. Just that, you have just put in the, quantum gates there and the loss functions, that all. That's all. Uh, okay. Again, we need to find a few more losses. I mean, a few more functions, which is now the discriminator loss, right? So we need to, define, I mean, get the discriminator loss first, right? So if you see here, the discriminator loss is exactly what we are, you know, creating here, right? So first we are calculating discriminator with generated data. We are getting that discriminator's output on the generated data, or discriminator fake output basically means discriminator's output on the fake data. And then we have generate discriminator with true data, which is discriminator with uh, true state. We calculate both of them. So discriminator fake output is this basically, cat phi g, and discriminator true output is, cat phi t, right? Substitute, and you calculate this LD loss function, which is the loss function for the discriminator, right? So that's the part for the discriminator. Come to the generator now. Discriminator with generated data only, right? So that is the loss for the discriminator. And let's define it. We have already defined it. Let's run it. Okay. So now we are about to start the training loop. The first step, as always, define the weights. As you remember, our generator had only three weights, right? Theta, phi, delta, only three values. So we are just randomly generating three values, creating them as the weights for generator. Discriminator, on the other hand, if you remember, it had number of repetitions plus one layer. Remember, whatever the repetitions you had, we were adding a final layer, extra layer at the end, because you don't end with a entanglement block, right? You end with a variational layer. So that's why number of repetitions plus one into number of qubits into three. Let me explain each of them. So I think I explained number of repetitions plus one part. Number of qubits, obviously, number of rows you have, right? Now into three is because that, we are having that multiple layers, right? First we have Rx and Ry, and then again Ry. So we have three layers for, for in one block this time. So if you remember our PPT presentation, we were just having one, in one variation layer, there was only one block of Ry, right? Here we have Rx and then Ry and then Ry, right? So there are three of them, and that's why you have that extra into three here. Okay. So we have defined the weights. Similarly, let's define the optimizer. So you will have a different optimizer for generator and a different optimizer for a discriminator. Okay, we have defined it. It's going a little slower. Mm. I'm still there, or my screen is frozen, or
Yeah, your screen is visible, but if you can scroll up or down so that we may know if it's frozen or not.
Yeah, screen is frozen, I think.
Everyone, kindly wait for the second while he joins back. I guess he was having some network issues.
Hey, uh, my system just crashed, right? So it just got hang. Let me just reshare the screen, right? And let me just turn off my video for now. Then once we have questions and everything, I'm audible, right? Yes.
Yes, yes, you're audible. Yeah.
Oh, great. So my system just crashed, because of the video and everything was on. So let me turn off the video for now. Let me complete the collab part, and then for the questions, I'll turn it on again.
Sure.
Just a second, let me open the collab. Let me share the screen again. Yeah. I'm sharing the screen. And so we were on the weights initialization. Okay. Okay, so the state has been restored to this state. So once we have already defined the weights, and I told you why and how we defined the weights, by the size of the weights. So we just then initialize the optimizers. For generator, you have a separate optimizer. For discriminator, you have a separate optimizer. Just define the optimizers, right? And notice that you are providing the weights for to each of the optimizer, like the corresponding weights to the each optimizer. Now here comes your training loop, a very simple training loop, right? First of all, here you are just creating lists to store the losses to visualize it later on. Then in the number of training cycles or epochs, whatever you name it, you are looping it over. And here in the first step, it's just the optimization for the discriminant, right? So here what you have is, first you just do the zero grade for the discriminator optimizer, obviously a standard PyTorch step, right? Then you have this discriminator loss function, remember? So you have, the generator being applied and the discriminator being applied, and, you get the discriminator loss. Just do the backward, so by preparation by gradients. Opt D dot step, which is basically, the step for the discriminator optimizer, right? So it's a very standard script, standard PyTorch script, right? And another thing, if you remember, while defining the, Q node, if you remember, we had kept interface equal to torch, right? And that's why if you see here, we are directly using torch to initialize the weights, right? So because while defining the Q node, we had already told Penny Lane that the weights you will coming may would be of of type torch tensors, right? That's why we had this interface equal to torch. Similarly, if you are using TensorFlow, for example, your interface will be then TF. I guess that's the keyword. So interface is TF. That's important to define there, right? Okay. So we've done the optimizer. I mean the loop for the discriminator. It's time to go for the generator. Again, zero grade generator loss, base emitter and base discriminator losses. The optimization step for the generator, generator optimizer. Append losses, and for after every 20 epochs, just print out the losses. Now let me just run this, and it will obviously take a little time to actually get all the results. But while it comes, I can just show you what it would sort of look like. Obviously, you can see it's really noisy, right? It's difficult to say what it's learning. It's hardly learning, right? And this is actual plot we'll see. I mean, and that's the good part of setting the seed, that I can just show the results before the entire thing runs. Because I've set the seed, so things will be the same, right? So here you can see the loss is not going really well. There are multiple reasons for that. If you see, and should I tell them, or you will try to figure it out yourself as an assignment? What should I do? What you guys say? Anyone tell? Okay, sure. So remember in the slide I told you that if the discriminator and the generator are not of equal power, sort of not equally powerful, then there will be problems, right? If you see here, your generator is just a simple U3, right? And the discriminator, they've applied 3-layer RX and RY, three layers, actually 4 layers, and entanglement blocks is too heavy of a network, right? So what you can do is eliminate Rx, go for R by Rz, I guess. Eliminate entanglement blocks if required, right? You probably don't need entanglement blocks here. If you look at the uh, the problem statement, it's most likely that entanglement is not going to help you here, right? So entanglement doesn't make a lot of sense here because it will limit it, right? The state space here. And you're using too big of a network for a problem that you probably don't require that big of a network. And that's why you see this sort of, losses not going well, training not going well, right? But this is very simpler problem that I had showed you. But the reason I showed you this that, because, no matter what your background is, computer science or physics or whatever, I would say this was still too, easy to follow along, right? And I also wanted to show you the example of what a, you know, playing around with quantum data and quantum network looks like. So, in the entire presentation in the previous session, I just talked about, classical data and quantum networks. So here, this was an example of having to, deal with quantum data and quantum network kind of setting, um, right? But I would say as a sort of assignment to sort of do something actually, what do you say, real world sort of thing. I would say take Penny Lane dataset. So Penny Lane has a lot of data sets inbuilt, right? Just like scikit-learn, right? And if you remember, I told you that Penny Lane is focused on quantum machine learning and quantum chemistry, right? So there are a lot of quantum data sets, quantum chemistry related data sets here. So what you can sort of try to do is using this quantum GAN concept, using this notebook as a reference, you can try to generate molecules with certain properties, right? So generator then would not be a simple U3 gate, right? It would be something else, right? Then you can try to do this, try to solve this problem of using a quantum GAN to generate molecules with certain set of properties or something of that sort, right? And that would be a sort of solving a real world problem. And this example that I showed you is a simple, hello world to quantum GAN. And objective here was just to, even if you are not aware of what is a GAN, right? Still, I should be able to explain you what is a classical GAN and how quantum GAN works, right? And I hope I was able to though. And I would, and the floor is now open to questions and also feedback that you would like to give me that, how the session was for you. Did you understand? Even if you don't understand, did you enjoy it? I would like to hear all of it. Okay, let me open the. There are something going on. Since modern MLDR models have large parameters, but since currently one computer has approximately only research phase knowledge representation. Okay, that's a good question. And obviously, see, I'm a quantum machine learning researcher, so obviously it's not like, if I'm working in a company, I'm just not doing research, right? Obviously, the objective is to put it in production, but there is to be a clever way around of doing things, right? Things might not be super straightforward of right. Things are not super straightforward on, based on just the size of the qubits or so, right? Um, but yes, it can be put in production, and that's my goal, right? So as a professional, you must chase some goal, right? Of what keeps you excited, what you makes to put in efforts into a subject, right? So the goal for me is to commercialize quantum AI, right? And that's the goal. And yes, we don't have 1,000 qubits, but there's always a good turnaround, a play around for that. Any questions? Anyone has? Even like for the session, previous session. Yeah.
Hey Jay, first of all, thank you so much for your session. It was, though I was lost in between, but definitely at the end of the day, I got the crux. And it's engaging, like even I'm trying to explore more on the quantum. Um, so a couple of questions I have, and pardon me if like it's out of the, not from the session, but it's more, first of all, it's like, you said something, right? Like initially that for the simulation, there is a limit. We can explore only to certain qubits. Beyond that, we have to run on the actual computer. So what was that limit?
Around 8 or 10 qubits or so. If you have GPUs, you
Okay.
still might be, but that would go in hours then. If you're
I see.
simulating it local simulator. So then, see, there are also types of simulators. So for example, Bracket provides different simulators. Those are like very powerful simulators. And there you can, I think, simulate up to 30 or 31, 32 qubits there, right? But if you like the way IBM says, utility error and all, if your problem is going 50 qubits, 60 qubits and all, then and you have to go for the real QPU.
Okay, I see. Second is on your startup, like as your founder, and you are also doing simulation. So what is your working like? You're I'm not sure if you're still in the profit mode or what it is, but what is the costing you bear, and then how you manage this?
Okay. So see, as I think I told this in the session when I started, when I was introducing myself, that I hold two positions right now. One is I'm working as a quantum AI researcher at BQP, where the focus is on engineering simulations, and side by side I'm having this QRL, right? So right now, QRL is in a very initial research stage, right? So the thought process is not just profiting or those side, but I'm slowly building it. As I mentioned in that slide, that I already created a Python framework, URL QAI, right? That has I've already launched that. So you can just install it with pip, pip install QRL QAI. You can install it, and it's a very small step on a very long journey right now. So the yes, we are profiting, but we have something out that I can showcase, right? And right now the thought process is to make that software or the Python package more powerful with much more abilities, right? And as things go forward, then we'll also profit.
Thank you, thank you. And one last thing, as you projected, like this AI going to be commercial, and you have a vision that you will make it. So what do you think, 2 years down the line, that what you're doing will actually be, for example, pharmaceutical, you have a Penicillin, you gave the example, right? It has a chemical composition, all those things, right? Which you can play around. But how it going to be in production soon, how we can see it, and how, as a founder like you, right? Like if I want to do something on that, what is the path forward to it?
Mhm. See, I mean, it's a very. I think the answer is very similar to the way I said on how you must approach a quantum machine learning problem, right? Just I mean, I see a lot of people just plugging in quantum for the sake of plugging in quantum, right? And then you say that why the quantum's accuracy is not as good as the classical accuracy, because you're plugging it into the wrong problem. That's why that is my doing, right? So rather than focusing on the quantum algorithm, it's important to focus on the problem that you're trying to solve, right? So where the classical version is struggling, so whatever problem it is, right? So for example, I gave the example of pin, where I'm working with BQP, right? So pins don't generalize, they have so many issues, and that's where I brought in quantum for their unique ways of introducing weights and then providing a compact representation and those things, right? And that's where its accuracy improved, it generalized better and those things, right? So quantum would work, and it can be definitely, I mean, that's my goal, that I'll try to put it in production as soon as I can, right? But at the same time, it's really important that you use it where it's needed and not just use it anywhere. If you use it where it's needed, then definitely quantum AI can get into production, and it doesn't need hundreds and thousands of logical qubits and stuff.
Okay, awesome. All the best. Thank you so much.
Thanks. Okay, there's another question by Ronak Sen. Since there are many gates in QNN, but mostly ReLU is like standard in ANN. So what does that? It's change the functionalities. Wait, see, Ronak, ReLU is an activation function, right? What I showed you right now, all those gates and stuff, they are the quantum equivalent of the hidden layer. So, I mean, if you remember that picture I showed on the left, I was giving a, the comparative analysis between the artificial neural network, classical neural network, and the quantum neural network. Those neuron layers, the hidden layers, right? Those were the equivalents, right? The quantum hidden layer and the classical hidden layer. The way you apply non-linearity to or the activation function to a particular artificial neural network hidden layer, you can do so also with the quantum hidden layer. So for example, again, like going back to the QAPN part, right? So the paper I published last year, there we had a hybrid network that I already explained in the previous session, right? So there, for example, there we had a input layer followed by a quantum hidden layer, and then there were a couple of there was just one or two, I think, classical hidden layers, and then output layer. So for each hidden layer, we had an activation function, right? So it's the again, ReLU is standard for ANN, right? But the problem, the activation function, highly depends on the network architecture and the type of problem being solved. For example, again, let's talk about physics informed machine learning, where you are trying to solve some partial differential equation. There you can't use ReLU. Why you can't use ReLU? Because I mean, if you go for the second order differentiation, at least, then it got zero, right? The differentiation, even the first order or second order, these order of differentiations are important in the physics informed machine learning. Why? Because you are calculating the PDEs there as your loss function. So if you are using ReLU there, then those terms will get zero and training will not happen. So in physics informed machine learning, you can't use ReLU. There, the norm is tan-h function, right? So activation function keeps on changing with respect to your needs and the setting there. But quantum hidden layer actually attempts to replace the classical hidden layer, and activation function can still sit on top of it, right? And how would it change? I don't think so, because it just replaces the classical hidden layer. What it really changes is the way network learns, right? The way hidden layer, the way a classical hidden layer learns, and the way a quantum hidden layer learns, it's fundamentally different. And that's what I think it really changes. Yeah. Any more questions? I think you guys can raise hands, right? So if you learned anything new or cool from this session, just raise your hand. Just want to see that. At least 2, 3. Nice. And yeah, okay, thanks. So I think in the very first slide I showed you that I also have a YouTube channel URL, right? Yeah, thanks for raising hands. So I showed you that I have URL. So those slides that I showed you right now in the PPTs, those animated slides, they come from one of the videos, which is that sort of explains quantum neural networks in 3 blue 1 brown style animation. So people who are familiar with deep learning must be knowing the 3 blue 1 brown YouTube channel, right? So I tried to explain quantum neural networks in the same animation style. All right. So I mean, after this session, if you can definitely go there, check it out. I think it's a again, there I explained with animation the entire what we say, the angle embedding part, the hidden layer, what layers is going on, and then the final output layer, the training loop, everything with animation. So I think that feels sort of, the animation is sort of better than PPT explanation, I would say. And again, this was an online lecture, right? I mean, offline is I generally like offline. There I can write things on boards, and people are way more involved because this was a sort of mathematically intensive session because we did the for propagation by hand, and right. So next time maybe we can have an offline session where we can have things on site, and we can have.
Yeah, sure. We would love to host you once offline at the IIT Jodhpur.
Yeah.
Yeah.
Can you please share your YouTube channel's link on the chat box?
Yeah, sure. Just a second.